finding the equilibrium temperature when substances at different temperatures mix. Now, I'm going to show you like a generic way to do this algebraically, because once you've sort of done the proof once, you can just plug and chug into the equation. But it's important for you to be able to sort of follow through and do this yourself, okay? And of course, this is a specific heat capacity question, so you use the mass times the specific heat capacity times delta T to get Q. This equally applies to molar heat capacity, but you'd just be using N, the number of moles, times the molar heat capacity times delta T. So this all hinges on the basic principle of calorimetry, that Q for the hot object is going to be equal in magnitude and opposite in sign to Q for the cold object. So the object that is initially hot, I'm going to put the minus sign next to that just to show that that is losing heat and is being absorbed by the cold object, okay? So I'm just going to use QH and QC for hot and cold, okay? So we can write an expression then for Q of the hot object equals our mass of our hot object times our specific heat capacity of our hot object times our delta T of our hot object. Now, delta T is always T final minus T initial, okay? So both of those objects are going to have a different initial temperature, but they will both have the same final temperature, okay? So this is where it's useful. Instead of saying delta T, you're going to say TF, and TF for the hot object and the cold object is the same. So I'm just going to leave it as TF minus the initial temperature of the hot object, okay? Ooh. And we can do the same for Q of our cold object. Q of our cold object is the mass of the cold object times the specific heat capacity of our cold object times final temperature. It's the same for both, minus the initial temperature of my cold object. Okay, so you can see where we're going here with this, that we can set minus Q for the hot object equals to Q for the cold object. Okay, so minus, oh y'all, hang on, see if I can do this smart. Minus Q for the hot object equals Q for the cold object. So now all we have to do, she says, is just like multiply out and rearrange that and then solve for TF, right? That's all we have to do. It's just time consuming. It's not difficult algebra, but it's just time consuming, right? So we end up with minus MHCSH. Geez. TF, right? Minus times a minus is a plus. Ha ha. MHCSH TIH. I feel like this is implying that I enjoy algebra far more than I do. Okay, and then on the right-hand side, we have MCCSC TF minus MCCSC TIC. So I want to get my TFs on the same side. So the easiest way to do that is see this guy right here with the minus sign. I'm going to make that go over there because why not? Okay, you know what? I'm just going to take this whole thing and just copy and paste. That's going to be like the easiest way to do this, I think. All right, so yay, keyboards. Okay, so if I take this to the right-hand side of the equation, it is now no longer a minus, it is a plus. Algebra is so much more fun when you can do that. And then if I want to take this over to the other side, I'm going to get rid of my minus sign. Oh, please drop it in the right place as well. So that makes life a lot easier, right? So I've got TIs on one side, TFs on the other side. So then I can take my TF out. Again, I'm just going to, oh, look at this. It's so much easier than typing it all out again. You know, when I do this on the board, I have to like shake my arm off to sort of like, yeah, relax a bit. Okay, so I can take this and take the TF out of the bracket, like so. But remembering that I copied and pasted that, right? So I can do that. Isn't that great? And then TF equals bum, bum, bum. If I take this side and divide it by all the things in brackets, I will get an expression that is generic in terms of TF and the mass of my hot thing and the specific heat of my hot thing and the mass of my cold thing and the specific heat of my cold thing. Like so. So I can do that. Just as a like FYI, we could have done the same thing for molar heat capacity and stuff, right? So then instead of being the mass of the cold thing, it'd be the number of the moles. It'd be my molar heat capacity, right? So just so you've got that somewhere that you can kind of refer to. There it is, number of moles, molar heat capacity, number of moles, molar heat capacity. So that's just, you can keep that one for free, okay? So anyway, back to the problem at hand, which was solving for my final temperature. Okay, so the mass of the cold thing, let's see, what was hot and what was cold? I think the water was hot and the iron was cold. Okay, doesn't matter as long as you pick one and you're consistent. Okay, so the mass of the cold iron was 24 grams. This is going to be horrendous to put in my calculator. The specific heat capacity of the iron was 0.449 joules per gram per degree Celsius. And then my initial temperature of my iron was 7.2 degrees Celsius. Right, so you can see how that's all going to cancel out. Beautiful. Right, then the mass of the hot thing, 100 grams of water. Lovely. The specific heat capacity of water. Oh, it doesn't say it. Good job, I remember it. 4.184 joules per gram per degree Celsius. Sometimes Alex just makes you just work, just to prove a point or something. I don't know. Then the initial temperature of the water was 50 degrees Celsius. And of course, I'd run out of room because that's just the way the cookie crumbles. Right, I think we just about get away with that. And then we're going to divide all y'all by the mass of the cold object. So it's 24 grams of iron times specific heat capacity of the cold object, 0.449 joules per gram per degree Celsius. Plus, I guess I should put my parentheses in and stuff. Start as you mean to go on and all that. The mass of the hot object, which was the water, 100 grams times 4.184 joules per gram per degree Celsius. Gonna put my line in there. All right, so this is definitely going to come out in degrees Celsius. But can I put in enough parentheses to make my iPhone calculator accept what I put into it? Who knows? Right, open parenthesis, 24 times 0.449 times 7.2, close parentheses, plus, open parentheses, 100 times, well, I didn't even accept my 100. Oh, this is going to go wrong already. 4.184 times 50. I think that's 20,000 on top. Let me try again. I should really pause this one, trying to make my calculator work, shouldn't I? 24 times 0.449 times 7.2 plus. Oh, I'm going to pause this because this is boring for you. Okay, it definitely took me a couple of attempts to make my phone calculator get that. It's much better on my own calculator, but I got 48.9 to 3 sig figs degrees Celsius. So whenever you solve one of these problems, like I know it's a lot of algebra and stuff, it's definitely a smart idea to relook at the question. Okay, so the water starts at 50 and the iron starts at 7.2. The temperature has to be between 50 and 7.2. There is 4 times as much water as there is of iron, and water has a much higher specific heat capacity. So it's likely that that final temperature is going to be closer to the initial temperature of the water than it is to the initial temperature of the iron. And look, it's close to 50. So I'm happy with that, and you should be too. All right, that'll do. So do the algebra at least once, just so you know you can do it, and then you can just plug and chug.